How to compute curve numbers. Here we have an existing stormwater project with several subbasins that make up the drainage area. These subbasins were created using the delineate subbasins command, which is covered in a separate tutorial video. If you haven't covered that step yet, you might want to start there. The link is in the corner of the screen and in the video description below. In this tutorial, we will focus on computing and assigning curve numbers for each of these subbasins. But before we get started, let's take a moment to explain what a curve number is and why engineers use it in stormwater modeling. What is a curve number? A curve number is simply a way to estimate how much rainfall will soak into the ground and how much will become surface runoff. It came out of the USDA Soil Conservation Service's research from the 1950s, and it is still widely used today because it is simple, familiar to engineers, and ties together land cover, soil type, and drainage conditions in one easy-to-use value. In practical terms, a lower curve number generally means more rainfall is expected to infiltrate into the ground, while a higher curve number means more runoff is expected. That makes it a convenient tool for comparing different site conditions, such as wooded areas, lawns, pavement, compacted soils, or developed land. While it won't capture every detail of how water moves across a site, it gives engineers and modelers a solid, reliable starting point for estimating stormwater runoff. Now that we have a clearer picture of what curve numbers are and how they work, let's go ahead and compute them for our subbasins. Using the compute curve number or compute CN command, we are going to head over to the watershed ribbon menu. This ribbon menu contains many drainage-related commands, including the compute curve number or compute CN command. Clicking on this command opens the compute curve number dialog box. In this dialog box, you see the select subbasins section. Here you will see a list of all the subbasins that are in the current scenario. In most cases, you will want to select all of them when computing curve numbers. The software will then compute a separate curve number for each subbasin. However, later on in a project, you might want to recompute the curve number for a single subbasin for whatever reason. You can select the subbasin directly from this table or click the Pick button. This will temporarily hide the dialog and allow you to select subbasins interactively from the map view. After you've made your selection, right-click and choose Done from the displayed context menu. In this video tutorial, I am going to compute the curve number for all subbasins. Now that we have selected the subbasins, let's define the other information needed for this command. Land use and soil data. To compute a curve number, we need two main pieces of information: what is on the ground surface and what is underneath it. The first piece is the land use or land cover. This describes how the ground surface is being used or what is covering it. For example, the area might be forest, pasture, open space, rooftops, roads, parking lots, residential development, or commercial development. Each of these surfaces responds to rainfall differently. A wooded area may allow more rainfall to soak into the ground, while pavement or rooftops will produce much more runoff. The second piece of information is the underlying soil data. Soils are commonly grouped by how quickly they allow water to infiltrate. Some soils drain very well, while others absorb water slowly and generate more runoff. Once the land cover and soil group are known, they are used together to look up the corresponding curve number value from standard curve number tables. In other words, the curve number is not picked at random. It is selected based on the combination of the surface condition and the soil's infiltration characteristics. For example, a grassy open space on a well-drained soil will usually have a lower curve number, meaning less runoff. That same grassy area on a poorly drained soil would have a higher curve number. And if the area is paved, the curve number would be higher still because most of the rainfall becomes runoff. The Land Use Data panel contains 3 subpanels, each offering a unique way to bring land cover information into your model. Land Use Data, NLCD layer. The first subpanel is NLCD layer. For projects in the United States, this uses the Online National Land Cover Database, or NLCD, to classify land types across your project area. For projects outside the United States, the software can access other available online land cover databases for many countries around the world. The content of this subpanel will automatically update based on the database available for your specific project location. The purpose of this layer is to identify the land cover categories within your watershed and assign curve numbers based on the corresponding hydrologic soil groups. Looking at the table, you'll see a range of land cover categories. For the NLCD dataset, this includes open water, developed areas at various intensity levels, forests, grasslands, agricultural lands, wetlands, and many others. Each category has different curve number values for each soil group, reflecting how much runoff that land type is expected to generate under different soil conditions. For example, a heavily developed area will typically have a much higher curve number than an undeveloped forest, because pavement and rooftops do not allow much rainfall to infiltrate into the ground. One important limitation to understand is that these online land cover databases are typically pixel-based data sets. Each pixel represents a certain area of land. For large regional-scale watersheds, this level of resolution is often perfectly adequate. But for smaller or more complex projects, where you need precise land use boundaries, the pixel size may not capture enough detail. In those cases, you may want to use your own GIS land use data instead, which is what the next subpanel is for. Land use data, GIS Polygon layer. The GIS Polygon layer subpanel is where you can bring in your own detailed land use data. For most smaller or site-specific projects, this is the recommended approach. Unlike pixel-based land cover data, GIS Polygon data gives you precise vector-based land use boundaries. That means you can better capture the actual land use conditions across your project area, especially when you are working with roads, buildings, parking lots, landscaped areas, open space, or other detailed site features. The software includes several commands in the Map Data ribbon menu to help you create this land use data. The first option is the Draw Land Use command. This allows you to manually define land use areas directly on the map view by interactively painting in the land use boundaries. Another option is the Classify Land Use command, which takes a more automated approach. It uses AI-powered image analysis to review the aerial-based map and assign land use categories based on what it detects in the imagery. But the command I find especially useful is the Automated Land Use command. This command uses alternate mapping source data, along with a predefined machine learning algorithm, to automatically generate detailed land use polygons with very little manual effort. On more complex projects, this can be a major time saver. So if you have not yet created your land use layer, set that up before returning to this dialog. We cover the automated land use command in a separate, dedicated tutorial video. If you are starting from scratch, I recommend watching that video first. You can find the link in the video description below. Land use data, default values. The last subpanel is default values. This option lets you assign a single default curve number or a single standard land use classification across all selected subbasins. This can be useful for quick estimates, early planning studies, or projects where the same general land use applies across the entire area. Just keep in mind that it is a simplified approach, so for more detailed projects, you will usually want to use either land cover database data or your own GIS Polygon layer. That covers the land use data panel and its related subpanels. Now let's move on to the second major panel, hydrologic soil type. Understanding hydrologic soil groups. The hydrologic soil type panel also includes 3 subpanels. But before we step through those, let's first talk about what hydrologic soil groups actually mean, because they have a direct impact on the curve numbers that get assigned. Soils vary a lot in how quickly they absorb water. In simple terms, some soils allow rainfall to soak in very quickly, while others resist infiltration and produce more runoff. The NRCS classifies them into 4 groups, A through D. Group A soils are the most permeable. Think of sandy soils like what you might find near a beach. If you pour water onto sand, it soaks in quickly and very little water runs off the surface. Group D soils are at the opposite end. These soils have very slow infiltration rates and often contain a high amount of clay. Clay tends to hold water rather than letting it pass through, which means more rainfall becomes surface runoff. Groups B and C fall between those two extremes. Group B soils allow moderate infiltration and may include sandy loams or silt loams. Group C soils have slower infiltration, often with more clay content and less ability to absorb water. So as you move from Group A to Group D, the runoff potential increases. And because curve numbers are used to estimate runoff, the hydrologic soil group plays a key role in determining the final curve number value. You may also see dual soil groups such as AD, BD, or CD. These are typically used for soils that behave differently depending on drainage conditions. The first letter represents how the soil would behave if it were properly drained. The second letter, usually D, represents how the soil behaves in its natural, undrained condition. So for example, an AD soil could behave like a Group A soil if it has adequate drainage, but like a Group D soil if it remains poorly drained. Now let's look at the first subpanel, the NRCS layer. For projects in the United States, this subpanel pulls soil data from the online NRCS soil survey database to determine the hydrologic soil group across your watershed. This is usually the most common and efficient approach for US-based projects because the data is already available and can be applied directly to your model. For projects outside the United States, the software can provide access to similar online soil survey databases from other countries and regions. Just like with the land cover panel, the available options will automatically update based on your project location and the soil data available for that area. The second subpanel is the GIS Polygon layer. This is used when you already have your own soil map data. For example, you may have soil polygons from a local agency, a regional database, or a data set that your team has already processed for the project. In that case, you can use your own GIS soil layer instead of relying on an online soil database. The third subpanel is default value. This option lets you manually assign a single hydrologic soil group across all selected subbasins. This can be useful for simplified analyses, early planning studies, or situations where you do not yet have detailed soil data available. So at this point, we have defined the 2 key ingredients needed to compute curve numbers: the land use or land cover data and the hydrologic soil group data. Before we compute the curve numbers, let's look at one more important section, the intermediate results panel. Computing intermediate results. When the software computes curve numbers, it is really combining 2 spatial data sets, the land use layer and the hydrologic soil group layer. In a real watershed, those 2 layers can overlap in many different ways. For example, you might have urban land use on Group A soils in one part of the watershed, the same urban land use on Group B soils somewhere else, and then again on Group C soils in another area. Each of those combinations can produce a different curve number. That is where the intermediate results option becomes useful. When this option is enabled, the software creates separate GIS polygons for each unique land use and soil group combination across the selected subbasins. So instead of only seeing the final composite curve number for a subbasin, you can look behind the scenes and see exactly what went into that calculation. You can see which land use types were used, which soil groups they were paired with, where those areas are located, and how much area each combination represents. This is helpful for checking your work, documenting your assumptions, and creating engineering exhibits. For example, you can export these intermediate result polygons to CAD or GIS and create a map that clearly shows how the watershed is divided by land use and soil type. To turn this on, check the Compute Intermediate Results checkbox. You can also choose whether the results should be automatically loaded into the project after the computation is complete. Then use the Browse button to select where the intermediate results should be saved. Now that the land use data, soil data, and intermediate result options are set up, we are ready to run the curve number computation. Computing curve numbers. Once you have selected the subbasins and configured the land use and soil datasets, click the Compute button. The software will then evaluate each selected subbasin and calculate the appropriate curve number based on the data you provided. When the computation is finished, the software will automatically fill in the curve number with the computed value for any stormwater method in your model that needs it. You can also review the curve number results directly in the dialog for each subbasin. When you are finished reviewing the results, click Close to return to the main project view. Reviewing the final results. After the computation is complete, take a moment to review the results in the Map Data Layers panel. You'll see that the software has downloaded the land cover data and soil survey data for your project area. You can expand these layers to review their legends and get a better understanding of how the data is distributed across the watershed. If you enabled intermediate results, you'll also see a separate intermediate results layer added to the project. Expanding that layer displays a legend showing the different land use and soil group combinations that were identified within the selected subbasins. To make the intermediate results easier to see, you may want to turn off the other background layers that you no longer need to display. This lets you focus directly on the intermediate results in the map view and clearly see how the watershed was broken down spatially. You can also review the same information in the Data Explorer tab. When you select the intermediate results layer, the attribute table will show detailed information for each polygon, including the land use type, the hydrologic soil group, and the related curve number information. This is a good final check before moving forward. It lets you confirm that the land use and soil data were applied correctly, that the spatial breakdown makes sense, and that the computed curve numbers are based on the data you intended to use. And that's the basic workflow for computing curve numbers for your subbasins. Once the values are assigned, they are ready to be used by the stormwater methods that depend on curve number data. From here, you can continue with your hydrologic analysis, knowing that the curve numbers have been computed consistently from your selected land cover and soil datasets.